Okay, so we resume this morning's session with the last speaker of this morning, Sakshi Jain from University of Rome Tor Vergata, and she will talk about discontinuities cause essential spectrum.
Thank you for having me and the organization of this meeting. I will be talking about our recent work, which is a joint work with Oliver Butterly and Giovanni Canestrari, who are my colleagues at Tor Vergata. And it's called Discontinuities Cause Essential Spectrum. So I will start with some introduction. So let's consider a dynamical system. So by that I mean T is a function on a space which is, let's say, a smooth manifold X, and mu is an invariant measure. So T star mu is mu, which I, like my professor, cannot decide if it is push forward or pull back. But anyways. Okay, and then I would call the system to be mixing if for every pair of functions in C infinity x, this integral converges to the pairwise integral as n tends to infinity. Then this system will be called mixing, but in dynamics we are rather more interested in seeing how fast does it converge, so which is called as rate of mixing. And so I would say the rate of mixing is defined as if there exists some lambda less than 1, such that for again every pair of observables in C infinity x, there exist these constants CFG, such that this quantity is less than equal to CFG lambda to the n. Then I would say that the rate of mixing is exponential, for example, in this case. Why is it interesting is the next question, but let me introduce one more definition which is very basic and important as well. Resonances, which I have not really cited where does it come from, but it comes from works of Roelle and Polycott around 90s. We say T admits, this system admits a Roelle-Polycott resonance or a spectrum if there exist complex numbers lambda j's. These numbers lambda j's, which have multiplicities mj's, and the I didn't write, but these lambda j's must have these lambda j's must have their modulus in 0, 1. I would say it admits Roelle-Polycott resonances if for every epsilon positive and for every pair of functions in C infinity x, this integral can be written as this sum, where nk refers to the Jordan blocks of these of the respective eigenvalues, and Cik's are bilinear functionals and in F and G. And here I mean to say that for every epsilon, this thing, there are finitely many lambda i's that I can write this sum. Okay, and these resonances can be studied with many different methods, and one of our favorite method would be transfer operator technique in Banach spaces. Maybe I give a picture of how these resonances might look like. I am not very good at drawing, but these are eigenvalues, so they might be here, and this order of epsilon n, by this I mean a small circle which has continuous eigenvalues, let's say. And in general we would like this okay, so when there is such a situation, I would say that this is decay of correlations if this epsilon can be made as small as we want. So if I can make this circle, make this disk as small as I want by choosing appropriate Banach spaces, appropriate spaces of these functions. I might have confused you a bit, but I'll try to make it clear in my next slide. I'm sorry about that. Okay. No. So I will try to make it clear with a very simple example, which is the doubling map, our favorite in a way. For this map, if we study resonances, I would say that for every epsilon positive and observables in C infinity S1, there exists C such that this condition holds. That with that I mean that there is a decay of correlation with exponential rate. So this particular thing can be studied by transfer operator, which I introduce here. So an operator from CR to CR, which is in this case I define as LGX like this, which is the transfer operator associated to the SRB measure. And if I try to study its spectral decomposition, it really lends me studying the decay of correlation. So the spectrum of L restricted to CR will be given by the point spectrum. I'm sorry about this, all the mess that I'm making.
Probably you have to click on the signal.
Yeah, but
to activate your pen.
yeah, thank you. In this case, if I study the spectrum of the transfer operator, it would look like this. If this is the circle of radius 1, then it has a eigenvalue at this place, which is 1, which comes from this fact that it's a norm calculated, the L1 norm calculated at L mu would be less than equal to mu, so it has one eigenvalue at 1, and then its spectral decomposition is given, its spectrum is given as 1 union a ball of radius half centered at 0, half to the r, where r is again the regularity of the functions here. And if I decompose do the spectral decomposition of the transfer operator, it would be P plus Q, where P is the projection on the eigenspace associated with the eigenvalue 1, and Q is the projection on the essential spectrum. So in this case, it is very much visible that if I increase the regularity of the functions under consideration, so the observables, then I can make this disk of essential spectrum go arbitrarily small as I want. So in this case, there is decay of correlation, which is exponential. So for every, if I consider my observables in C infinity r, it can be made as small as I want. But that is a very special case. That doesn't happen all the time. But there has been a lot of study in past decades about these problems, where we see the presence of resonances and the decay of correlations associated with the essential spectrum of the transfer operator, which I will bring in my next slide. Okay, so studying the spectral decomposition of this transfer operator, we can conclude about the decay of correlations, because this particular integral that we were interested in is also given by f ln g, integral of f ln g with respect to the Lebesgue measure, which is the invariant measure in this case. I will get that this particular quantity is less than equal to c half to the r to the n, so it can be made arbitrarily small if I increase the regularity of the functions under consideration. There has been a lot of work on these kind of problems, and trying to, because we really like to make the essential spectrum as small as we want. This is not something we like to have to persist. So there has been a lot of study in past decades. For example, I would quote just a few of them. In case of smooth uniformly expanding transformations, call it an isola. And for in case of smooth hyperbolic systems, Gazelle and Leverani in 2008, and for two-dimensional linear pseudo-Anosov maps for Gazelle and Lenu, have proved that the essential spectrum can be made arbitrarily small for likewise choices of Banach spaces. So it depends what Banach spaces we are choosing, but we can make the essential spectrum as small as we want in these particular cases. Also, this includes, maybe not very much clear, but it also includes the case of Markov maps, which can be considered under the category of smooth uniformly expanding transformation. So by Markov, I would mean the Markov expanding case, because in that case there are discontinuities, but they do not really persist because discontinuities map onto each other. So they are not really harming the system under consideration. But okay, then naturally the other question that arises would be that what if the system is non-Markov? So is it possible to find a Banach space for which the essential spectrum can be made as small as desired, also in the case of non-Markov maps? First, to answer the question, let's see how are things happening in the non-Markov case. So if I consider by non-Markov, let me say first what I mean by non-Markov here. So, sorry. I'm considering the simplest possible setting here. So I'm considering a two-branch map which has one full branch. So this is one, and another branch is not full branch but is still expanding. And by non-Markov, I mean that at least one of the discontinuities has its orbit which is infinite orbit. So for example, in this case, if this is the point A, then the orbit of A would be infinite. In such a case, I would call as a non-Markov map. And in this case, if I consider some function g in C infinity, and I'm considering C infinity because the last case told us that if we keep increasing the regularity of the functions, then it is possible to attain essential spectrum as small as we want. So let's start with the most regular functions. So if I consider g in C infinity and I push through it the transfer operator, which is given as this with a general weight phi, then we will see that it brings discontinuities in the points which are the images of this discontinuity of the function. And this height is basically given by this weight here. This height is given by this weight here. So studying this behavior of the action of transfer operator on a observable, we'll make two major observations. Okay. Make two major observations. One is generation of discontinuity. So the function that I push through my transfer operator, I see that it gets discontinuities at the points which are really the images of this function. So at TAs or T square A and so on, as how much the iterates of the transfer operator. And another is shift in the discontinuity, which is if I consider L phi g and I see its jump. Okay, let me first say what I mean by this particular quantity here, which is jump. For a function f, jump of f at x would be given by limit epsilon tending to 0, fx plus epsilon minus fx minus epsilon. I mean, I know everybody knows this, but just to remind. So this is the jump, and the two major observations is generation of discontinuity and the shift in discontinuity, which is given as the image of the previous discontinuity of the function. Here, L phi g. So the jump of L phi g at TKA would be given by this height, which is given by phi, the image of phi, times the previous jump. So there is a shift in the discontinuities. And these two observations help us conclude at least the fact that if we have to consider a Banach space for such a condition, such a system, then we should be allowing discontinuities of the observables at the points in this orbit, TKA. Keeping these two things, basically this generation and shift, these two observations are really crucial, and keeping this in mind, we move on to try and answer this question, and it motivates our first result, which is that for any t which is piecewise C0 and monotone on the interval, and phi which is piecewise C0 and bounded, then if our Banach space satisfies these three conditions, the C infinity is contained in B. This is again for the reason that we want to allow as much regularity as we can for the functions in B, and see if it helps decreasing the essential spectral radius. Other would be L phi extends to a continuous operator on B, which is obvious. We should have this, that the transfer operator is continuous on the Banach space. And this third condition, which is as of now very important, but is L infinity norm is bounded by this Banach space, which this condition we don't really like, but is there as of now. This should be true for every h in the span of L and C infinity. If these three conditions hold, and if there is a non-trivial discontinuity, so by non-trivial discontinuity I again mean that the orbit of the discontinuity is infinite. If these are the conditions, then the essential spectral radius has a lower bound, so we cannot make it as small as we want. So the answer to that question that we posed is really no, is negative. There is an essential spectrum which is persisting, and it has a lower bound for its radius. Okay, but now comparing some, because there has been work in literature which is about calculating the essential spectrum radius in such a setting. If we compare it with this, there is a result by Keller which is in the piecewise expanding case, and weight is 1 over t prime, so the one associated to SRB measure. This result is on the bounded variation space. The essential spectral radius in this case is given by this particular limit here, which is 1 over t n prime. So again, if this function is given, if this is the non-Markov function, that the system that we are considering, then the essential spectral radius according to Keller in case of BV is exactly given by this quantity. So it considers the least expansion of the function, and the lower bound that we have made is this, that on the max, this is the expansion on the non-trivial discontinuities and the maximum over all the non-trivial discontinuities. This is not infinity norm and this is infinity norm, so it kind of brings this thought that they must be relatable, and this must be less than or equal to this particular quantity, because this is supremum over every possible 1 over t n prime. So the next natural question would be that is it really true that there are systems for which these two quantities differ from each other, and if they are staying equal forever, then it doesn't really make any sense to talk about this. So the next question would be, does there exist T such that these two quantities are different and our lower bound is strictly smaller than Keller's bound? And let's remember that I give lambda k as Keller's bound and lambda is ours. And to answer this question, there is our next result, which says that for any C in 0, 1, there exists T such that the difference between these two quantities is greater than equal to C. So we can make these two quantities as apart as possible within the range of 0 and 1 by considering some systems. Okay, and this kind of gives the idea of the proof of this particular result. If we consider our non-Markov system in this setting, so it has a expanding branch but is not as expanding. So alpha is the slope here and is very close to 1, is greater than 1 because it is expanding but is very close to 1. Then there are other two branches which have slope beta and are close to infinity, so that this slope is really high, and there is this third slope which brings in the non-trivial discontinuity, so is in the non-Markov setting, and its slope is rho, which I will say what rho is in a few minutes. So in this setting, let's observe why this special kind of function I'm talking about. So here 0 is the fixed point, as we can see, and if we calculate first the Keller's bound, which is given by this quantity here, it considers the least expanding branch, so it considers the first branch, and its essential spectral radius is given exactly by 1 over alpha, and since alpha is very close to 1, 1 over alpha will be very close to 1 again. And now, to compute our lower bound, we first make some observations here. If I call this, okay, no, okay, this is omega 1, omega 2, omega 3, and omega 4. Then what I mean to say is that omega 2, the partition omega 2 and omega 3 have covering property, which means that T omega 2 contains omega 2 union omega 3, and similarly T omega 3 contains omega 2 union omega 3. It means that there must be points in these two intervals which stay within these intervals forever under the action of T. So their orbit stays only in these two partitions forever, and we want to choose the rho such that this happens for the image of 1 also. So what I mean is that this set remains within omega 2 union omega 3 forever for every k. If so is the case, since 1 is the non-trivial discontinuity and our lower bound really works on non-trivial discontinuities, so lambda is given by 1 over beta, and since beta is as close to infinity as we want, 1 over beta will be as close to 0 as we want, and so the difference between the Keller's bound and Keller's estimate of essential spectral radius and our bound would be as close to 1 as we want. So they are not really exactly the same quantities, then they can be made as far as possible within the range of 0, 1. But okay, this is true that these two quantities are different, but the question would be really that could there be Banach spaces which respect this bound? So the next question is, does there exist Banach spaces on which the essential spectral radius is equal to our bound, or at least closer to our bound that we have said, and is not exactly what was Keller's bound? And this motivates the third theorem, which says that for T to be C infinity piecewise monotone and uniformly expanding, and phi from 0, 1 to complex piecewise C infinity uniformly bounded away from 0 is an essential condition here. Then for every lambda tilde greater than lambda, there exists a Banach space such that essential spectral radius is less than equal to lambda tilde. So it can be as close to our bound as we want. They could be, we can make Banach spaces. I'm sorry about the next slide that I'm going to show, but is about the proof of theorem 1. So let me remind what theorem 1 was. Okay, so theorem 1 says that if T is a piecewise C0 and monotone map, and phi is piecewise C0 and bounded, then if our Banach space respects these three hypotheses and there is a non-trivial discontinuity with T, then the essential spectral radius cannot be made as small as we want, so it has a lower bound. And next would be the proof of this theorem. Okay, so let us suppose that we have a Banach space B which respects these three conditions. First is that C infinity is contained in B, and L phi is an operator from B to B, and that it bounds the L infinity norm. If so is the condition, I consider A naught to be the span of C infinity. I mean, I'm giving this idea of the proof in a very simple setting, is not the idea of the proof of the theorem as it is. So, okay, A naught I consider as the span of union L and C infinity, and A to be the closure, to be its closure with this B norm. Then for okay, let me say first what is really the idea behind the proof. I want to study the spectrum of the transfer operator, but to study the spectrum of the transfer operator, I would rather study the spectrum of the dual operator, dual transfer operator, because we know that the spectrum of the dual and the operator would be the same. Okay, so I am trying to study to see some linear functionals on A. For every lambda, I define these L lambda h, which are given as summation lambda to the k for lambda is smaller than R bound upon, if you remember, the shift in the jump. So this quantities comes from the shift in the jump, and then the jump HTKA, where jump again is the okay. So if this was an observable in C infinity, then it's jump. I apply transfer operator L phi on this, and I obtain a jump at TA. May look like this. So this height was given by phi A GA. Anyways, this I define these functionals L lambda as this, and we can see that if a norm of H infinity is bounded by the B norm of H, then L lambdas are linear functionals, so they belong in A star. So basically I need this condition here to call them the linear functionals, to call them the functionals in A star. So I will try to see if they are really the in the spectrum of the dual operator or not. Well, turns out that they are not really in the spectrum of the dual operator of L, but in some translation. So for that I define this operator K, which is defined as phi AHA for every H in A naught. And turns out that this is a compact operator, so it doesn't really mess with the essential spectrum. Okay, and M is defined as L minus K. Then the dual of M would be M star, and we see that these linear functionals L lambda are really in this spectrum of, so for M star L lambda H would be L lambda MH, which is lambda times L lambda H. So lambda comes out to, so these are serving as the eigenvectors of the dual operator, and so lambda for every lambda less than capital lambda will be in the spectrum of the dual operator. Since we know that the dual, the spectrum of the dual and the function are same, so this particular also let me emphasize this, that we know that for every lambda, now we know that for every lambda less than this quantity is in the spectrum of M star, and also since a spectrum of an operator is always closed, so also less than equal to this particular disk must be inside this spectrum. So we get that this set is in the spectrum of M star, which must be equal to the spectrum of M with the functional analytic things, and this implies that now we know we divide the spectrum in two parts really, point spectrum and the continuous part of a spectrum which lies in the essential spectrum. So this disk being continuous must be inside essential spectrum of M, and since M and T really differ by just a compact operator, it doesn't harm the essential spectral radius, so the essential spectral radius of L restricted to A will be at least lambda TA. Okay, and okay, let me say one more thing about this, that this idea of proof that I have given is particularly for this Banach space A, but it can be proved similarly for any Banach space B which contains A inside it. And in that case, we will need some more technicalities of spectral theory, the functional analytic technicalities of spectral theory, and we can still show that the essential spectral radius. Okay, I'll just say this. So in that case also the essential spectral radius of L restricted to L on the entire space B will also be greater than or equal to lambda. So the conclusion is that the essential spectrum cannot be made arbitrarily small even if we want. Okay, and this kind of is the idea of the theorem, the proof. I am not really giving all the technicalities. Okay, and now let's revisit what was the other theorem here. This theorem which says about the existence of the Banach spaces through which we can really realize the essential spectrum as close to our bound as we want. So T is a C infinity piecewise monotone uniformly expanding. Remember, let's observe that this particular theorem considers the hypothesis of expanding map, but that general theorem, the first result, was true for any piecewise monotone C infinity map. And phi is a complex function piecewise C infinity and uniformly bounded away from 0. Then for every lambda tilde greater than lambda, this essential spectrum can be realized. And I will say very little. Well, this particular result has a very technical proof, so I will not go inside the details, but let me say a few things about the norm, how we construct it. For any h in B zeta, okay, so I will call my Banach space to be B zeta R, this thing where R denotes the regularity, So R denotes the regularity of the observables in B zeta R, and the norm is given as a continuous part and a jump part because there are jumps. So this norm is really defined to respect the jumps, the discontinuities. So the continuous part of the norm is given as a summation of t from t equals 0 to R dAth, where by dAth I mean the weak derivative of h. And the jump part of the norm is given by sum from t equals 0 to R minus 1 dAth, and the jump norm, which is again given by this quantity here. And here these weights that I have combined with within the norm are again given by the shift in the jump. So those two major observations that I am sure everybody has forgotten by now, but the major observations, which are generation and shift in the discontinuity, really helps us defining the norm here. So with this norm, we were able to prove a Lazauta-Yorke inequality with B zeta and R norm as the strong. I haven't really made a slide for that one, but let me say what we have proved. Okay. So with this as the stronger norm, and I'm sorry, I didn't write what. So a Lizotta-Yorke inequality, which looks like this, which might not be very clear what I have written, but is with the stronger norm B zeta r and the weaker norm C r minus 1, and we get that the contraction coefficient in this Lizotta-Yorke inequality is lambda tilde, where lambda tilde is any number which is very close to lambda that our lower bound was, and so it gives us that the essential spectral radius would be close to this, less than equal to this lambda tilde. Also, we proved compact embedding between CR minus 1. I mean, there are some technicalities within the proof of this particular theorem which I would not like to go into, but this is what it is. And okay. Thank you.